Thank you all. And can I have the lights down, because I'm going to be showing some subtle EM. Great. And I wanted you guys to be able to see the detail. It's a thrill and very moving to get to talk to you all today. And I just want to say I've been moved all day long by the questions and comments from the audience. It's why we do this work. And so to actually be in this room with you is terrific. We've been trying to understand the prefrontal cortex in hope of coming up with new and better treatments for mental illness. We've already succeeded a little bit with one, which is why, I'm sorry. I'm pleased to say I have a disclosure statement that Yale and I used to get royalties. Intuitive is now generic, so it's a sentimental thing to say. But my interest in mental illness actually began when I was a teenager, and I volunteered at the State Psychiatric Hospital in New Jersey, Greystone, and spent the summer there. And it was an extraordinary experience because I really got to know several patients and to learn about them, their symptoms, what bothered them. And one of the most important things I learned about was the effects of stress on their symptoms. We already heard from Keith how the stress of his wife's miscarriage was a trigger for him. And I got to see this in a much less dramatic way in terms of the stressor, but in a very dramatic way for how it affected my life. One of the patients I got to know had schizophrenia, and he had been an astrophysicist. And we would have wonderful discussions about astronomy. And when we were talking about astronomy, he was completely lucid. You would never know that he was ill. And then one day, I happened to mention the name of someone at the hospital who was very cruel. And just this tiny stress of mentioning this person's name, this man disintegrated into what we call word salad, thought disorder, just from that tiny stressor. And then after a few minutes, as he relaxed again, his thought process coalesced, and he went on talking about the solar system. And that moment, I knew I had to study what stress did to higher brain function. That obviously it was something chemical going on that could produce something that rapid and that powerful. Octavio Paz wrote in a poem, "Suddenly there are moments that explode and become stars," and that was such a moment for me. And I've been studying stress and its effects on higher cortical function ever since. And when I say higher cortical function, I have focused on this brain region that we've been hearing about today, the prefrontal cortex. And this is the most newly evolved part of the brain. These are the circuits, that generate the mental representations that are our thoughts. And we often test these in the lab using working memory tasks. We heard earlier today that working memory deficits is one of the risk factors for descent into schizophrenia in those in the prodrome. And as I'll tell you in a moment, Pat discovered these circuits and how they create thought. And these are the foundation for abstract reasoning, for our executive functions, for the kinds of top-down control of thought, action, and emotion we were just hearing about from the last two speakers. And most in the very front, this is where we have our conception of a self, empathy for others. So our very highest order functions in this brain regions. And what I learned was this brain region is very rapidly taken offline during stress. And these are also the circuits that are most vulnerable in schizophrenia. So really important to learn about. So, for example, one important study has shown that hypoactivity of prefrontal cortex actually correlates with symptoms of thought disorder. So in patients doing a difficult working memory task, here's control performance. When it gets hard, the patients are having a rough time. Their prefrontal cortex becomes underactive, and the more underactive it is, the greater are their symptoms of thought disorder. So it was a very impressive link between this profound cognitive symptom and prefrontal dysfunction. And other research has gone on to actually see architectural changes. For example, gray matter loss in prefrontal. If you compare identical twins, this work happened to be by Ty Cannon. And you can actually see these waves of prefrontal gray matter loss as people descend into illness from the prodrome. Again, work from Ty Cannon's group with a consortium across the country. So this is obviously something really important for us to understand. What is causing this prefrontal dysfunction? So, and the two questions then that we've been focused on: how does the prefrontal cortex generate thought? And this, so much the work of Pat Goldman-Rakic, which I'm about to show you, and what makes these circuits so vulnerable to loss in schizophrenia. So one of the extraordinary things that Pat Goldman-Rakic did was figure out how the prefrontal cortex has the microcircuits to generate mental representations, being able to represent in our minds without any sensory stimulation. And she did most of this using a spatial working memory task, so visual spatial, representation. These studies required monkeys because rodents have very little prefrontal cortex. And in rhesus monkeys, at long last, we have these circuits that qualitatively are very similar to humans. And the monkeys do the following task. They fixate on a central spot, and as they're doing that, a cue comes on in one of 8 locations, so here, for just a half a second. And then the cue goes off, and the monkey has to keep fixating, but just remember what that location had been over many seconds. And then the fixation point goes off, and that's the cue for the monkey to now move its eyes or its hand, depending on the kind of task you're doing, to the remembered location to get a favorite juice reward. Now, what makes this task hard is that there are hundreds of trials, and the remembered location is constantly changing. It is, where did I leave my cell phone, reading glasses, car keys this time? Most of us cheat and always put it in one place. But this task, you can't cheat. You actually have to remember the constant updating of the contents of working memory. And as the monkeys perform this task, Pat Slab would record from neurons in the prefrontal cortex, and they found these remarkable neurons that have neural representations of visual space. So this is a neuron that fires across, this is the delay period. So the cue comes on, delay period, response. Every single time the cue had been at this location, so like here, this neuron fires like crazy. But if the cue was in any of these other locations, the neuron didn't fire. So at the end of the delay period, when the monkey has to make a response, if this neuron is firing, the brain knows, okay, it was here, look over there. Is that clear to everybody? And so this cell then is representing 90 degrees. It is allowing the brain to hold that information in mind. So that was a huge step forward to find that. And then Pat went on to discover the neuronal microcircuits in prefrontal cortex that generate this. They are in, deep layer 3, and they're called pyramidal cells because they're shaped like pyramids, and these are our GABAergic interneurons. What they really look like, this is one of her pictures, this beautiful pyramidal cell, and here the GABAergic interneuron. And for today's talk, we're going to focus on these pyramidal cells because what they do that's so special is they excite each other to keep information in mind even when there's no sensory stimulation. This is how we generate ideas, thoughts, without having to have the environment initiate it for us. And I'll be showing you in a moment that it's doing this through what we call glutamate NMDA receptors. And these pyramidal cells excite each other through connections on what are called dendritic spines. So do you see this looks like a branch with little twigs sticking out? Those little protrusion twigs are called dendritic spines. And human and monkey brains have just zillions of them for all the many connections that we have. And so these cells excite each other through connections on these spines. And the cartoon form of this that I'll be showing you will look like this, where cell number 1 excites cell number 2 on this protrusion of a dendritic spine. So this is what prefrontal cortex looks like in a control subject, layer 3. And this is now the work of David Lewis's lab. This is what it looks like in schizophrenia, this profound loss of dendrites and especially of these spines. So the cell bodies are still there, but the way they have to talk to each other is greatly diminished. So David's lab has recently shown that these pyramidal cells are profoundly underactivated. If you look at their mitochondrial enzymes, tremendously downregulated. There is this huge loss of connections, and what that would mean is this huge loss of persistent firing needed for strong mental representations. And you can see this in imaging studies as a reduced bold response. So what is causing this? And we have been studying prefrontal neurons to try and understand what makes them so vulnerable. So now, to do this quickly, I'm doing it mostly as a cartoon, where we're looking at how pyramidal cell neuron number 1 tries to excite neuron number 2 on the spine, and it does it using a chemical called glutamate. These are packets of glutamate that get released and try to engage and excite what's called an NMDA receptor. And if they succeed, it can excite the next neuron and keep the information going. So Bob Friedman this morning talked to you about acetylcholine and the nicotinic alpha-7 receptors. And what we have learned is they are essential for this process. So NMDA receptors will only respond to glutamate if they're sitting in an electrified membrane. And who electrifies the membrane for them in these special high-order circuits is the nicotinic alpha-7 receptor. So acetylcholine stimulates this receptor that electrifies the membrane, that allows these receptors to respond to the glutamate, and we get a connection made. And what's fascinating is that acetylcholine is released only when we're awake or when we're dreaming, not in deep sleep. And so I think this is one of the bases for consciousness, that we need acetylcholine to connect these prefrontal circuits and allow us to have conscious awareness. And we have been giving drugs that stimulate the nicotinic alpha-7 receptor to see how they affect these neurons. And the way we do this is we electrically sprinkle just a little bit of drug right onto the neuron we're recording from. And here you see a neuron that usually fires to this direction down here. It's not very good at it under control conditions, but you can nonetheless tell this is what it's trying to represent. When we sprinkle on a little bit of our nicotinic alpha-7 receptor agonist, so we're stimulating these receptors more, look how beautiful this is now. So a much stronger representation. Can you see how this would be much clearer information for the brain than that? Being able to truly hold information in mind. But dose is critical, because if you give too high a dose, then everything is getting this cell firing, and the information is actually lost. And I think this is one of the great challenges for drug development in this arena, that dose is essential, cognition is an exquisitely delicate thing, and we have to treat these circuits gently. So why this particular synapse is so relevant to schizophrenia, there are genetically linked insults to both NMDA receptor signaling and, as we heard from Bob this morning, to nicotinic alpha-7 receptors that increase risk of schizophrenia. And I think you can see why this would so weaken these circuits. And I have heard patients with schizophrenia talk about why they smoke, and that as they smoke, they feel themselves appear to themselves. And I have wondered if it's because they're strengthening this connection with the nicotine. And hopefully we can develop a therapeutic that does that without the ill effects of the smoke. So as he told you, medications are currently under development. Well, I want to go to the next stage of this, which is that the strength of these higher cortical connections is also very dynamically, very rapidly altered by potassium ion channels that are located on these spines. If you're interested, they're called HCN and KCNQ channels, alphabet soup. The main thing is that they can open, and when they do, potassium comes out, and that actually weakens this connection. And you need at least a little of this, because otherwise you have seizures. In a circuit where everybody's exciting each other, you need a little negative feedback or it will run away. And if you aren't able to do this, you have epilepsy. But who opens these ion channels are these intracellular messengers called cyclic AMP, which activates protein kinase A, and they go and open these channels. And why this is so important is these are the chemicals that are driven and activated by stress exposure. So what we have here inside these spines is what we call feed-forward calcium cyclic AMP signaling, where we get calcium release from, this is called the spine apparatus. It stores calcium. With stress, it gets released. That makes cyclic AMP, which activates protein kinase A, which then causes more calcium release, and we get this vicious cycle that can run away, rapidly open these potassium channels, and disconnect the network. And we think this has evolved like this to be very rapid, because danger usually happens quickly. The bear jumps out of the tree and lands in front of you very quickly, not slowly. That actually happened to me, so that is, do not walk silently through the woods in Vermont. Sing to yourself. But this idea that it might be helpful in many instances in danger to take this slow, thoughtful prefrontal cortex offline and very rapidly turn control over to our primitive brain circuits, which have the reflexes and habits to what I did with this bear, freeze, because bears can't see things that aren't moving. So the prefrontal cortex in me was blank except for the one word bear, whereas my more primitive circuits had me instantly frozen so that when the bear turned around and looked at me, it was amazing because it was only like 20 feet away. But because I was frozen, it didn't see me and it walked away. So, so primitive brain circuits are a good thing sometimes, but not when you're up talking in front of an audience or many other things, especially in modern life. And what we've learned is that these stress pathways, which, by the way, there's evidence suggesting they're increased in adolescence, which might relate to the kinds of things BJ was just talking about. You have to keep these under very tight control or you're in trouble, because then you're just going to have disconnection all the time. And in fact, we think that having insults to this is what makes these circuits so very vulnerable, and that with sustained stress or genetic insults that make it weaker, we get actual architectural loss of the dendrites and spines. And so we wonder if this is contributing in part to what we're seeing with the spine loss at the onset of schizophrenia. Thankfully, we have these built-in regulatory control mechanisms. I know these are big names, but they're kind of cute once you hear them over and over. So phosphodiesterase, PD4A, what it does is chew up the cyclic AMP and stop that vicious cycle and return things to normal. And it has to be in the exact right place. If it's over here, it's not going to be able to do it. And it's anchored in place by a protein called DISC1, disrupted in schizophrenia. And we know it's called that because this is a, the gene for DISC1 is altered in a large family from Britain with high rates of mental illness. I just want to show you a little of our immunoelectron microscopy that lets you know how we actually see that these things are here, because it's just so beautiful. So we have the glutamate packets being released at the synapse, and then here is the spine apparatus with all this calcium, and then here's DISC1 holding on to the PD4A to keep it right where it needs to be. Isn't that cool? And these, both PD4A and DISC1, genetic insults linked to high rates of schizophrenia. So we begin to have a sense of how we weaken these connections in schizophrenia. Now, luckily, we're also finding ways to strengthen these connections. Therapeutics, the noradrenergic alpha-2A receptor inhibits the production of cyclic AMP. These receptors are also right there. And the alpha-2A agonist guanfacine, when we give it onto these cells, enhances the firing. And when we give it systemically, it improves working memory, reduces distractibility, improves impulse control, all of this in monkeys. But based on this work, I'll show you in a minute, we're now using it in humans. But one more really important thing relevant to schizophrenia, when we give it to rats who are being chronically stressed, what we find is that guanfacine rescues this loss of dendritic spines. And we wonder, might it do the same in the prodrome? And I should note that guanfacine also is anti-inflammatory, and it inactivates microglia, and so might be helpful in that way as well. So guanfacine is now in widespread use for a number of prefrontal disorders. It was approved by the FDA under the name Intuniv for ADHD. It's first-line treatment for Tourette syndrome. It's being used to treat autism spectrum, and especially helpful in children who've been abused or traumatized. That work we're trying to continue at the Yale Child Study Center as well. It's being tested in mild traumatic brain injury to prevent substance abuse, helping that top-down control. Anesthesiologists use it to reduce inflammation and enhance connections as people come out of anesthesia, so treating emergent delirium, and evidence from London that it can help with infections to the brain. And my great hope that it really might be useful in the prodrome of schizophrenia to protect these precious prefrontal circuits. So closing with the acknowledgements, many people, Konstantinos in charge of the EM, Min Wang in charge of the physiology, and NARSAD essential, especially when we were just coming up with these ideas, beginning to see that these circuits are so different from classic circuits. No one else would believe it. NARSAD funded us. Thank you.
How about schizophrenia? How about depression and bipolar?
I don't know if anybody has been trying it. I don't think in depression. I don't know of any studies. I think it's often given to kids who they thought had ADHD, but actually were bipolar and found it helpful.
Yep.
I just wanted to say that my family member has had a severe depression from past several years, and he tried the Vibrate. It's like a miracle. The depression just went away, and it's like it's like a miracle.
He had what to begin with?
He suffered with the depression for many years.
And he took Intuna?
He took the Vibrate, the medication, the new one.
The guanfacine?
No, Vibrate.
Yeah,
I'm not sure.
I'm not.
Yeah, so anyway, so was that helpful when he took
His depression went away. It's like 95% of his depression disappeared.
Thank heavens.
Yes.
That's great news.
He's like a new person now.
Thank you.
This is why we do medication development. You know, it's so sad that it's become medication like evil, especially if you read the New York Times. Medication's evil, and yet really, hopefully, they really rescue people.
Hello?
Yeah, well, you're on.
Is there any correlation with your studies with what happens with the onset of elderly problems, dementia?
The onset of what?
Dementia?
Oh, yes, actually, that's a whole area of research in my lab, that with aging, we lose that cute PD4A. It's unanchored and not there, and it leads to increased phosphorylation of tau, which is the precursor for neurofibrillary tangles, which is one of what kills cells in Alzheimer's disease. So, so very relevant to this. And also what we see just with normal aging, beginning in middle age, is these cells can no longer keep firing because of the loss of the PD4A. Those potassium channels are open. But if we give guanfacine or things that block those potassium channels, the firing returns. So a bunch of us take guanfacine already.
Wow.
That's
Question.
how I could remember the talk. But
I have a question here. Hello.
Careful there.
Could you please wonderful presentation, really
Thank you.
fantastic. Would you please comment on the role of the D1 dopamine receptor in cognitive dysfunction, because it signals through cyclic AMP. I realize it's a slow synaptic process versus these rapid ones.
Oh, good.
But
I
could
still
you
have
comment,
this on
please?
here. Yeah, actually. Yes, my lab has been studying the dopamine D1 receptor since I first came to work with Pat, so for decades. And it does indeed activate this signaling pathway, and it disconnects the networks. So at an optimal level, meaning a low level, it's doing this for the noisy connections, what we call the non-preferred connections. So it allows the neuron to have much more narrow tuning. It's more refined. So we call these the sculpting actions. But during stress, you get high levels of dopamine release, and that's exactly what's happening here. Dopamine D1 disconnects everything, and prefrontal goes offline. So it's a narrow inverted U, and I think we all experience this ourselves when you go from pressure you can handle, a narrowing of focus, to uncontrollable stress where now you can't focus at all. So,
Thank you.
but it's the challenge for making D1 agonists for the treatment of schizophrenia. The one other thing that D1 receptors do, they phosphorylate the NMDA receptor and keep it in the synapse. And so the hope is that you can have gentle D1 agonists that do this and do this mild sculpting, but don't have stress-like effects. Yeah, so I think there's some companies going that route.
What are your thoughts on TMS?
Um,
Your thoughts on TMS?
TMS for
Yes.
So transcranial magnetic stimulation for treating mental illness. So I'm not a clinician, so I can only talk about it in theory. I can imagine if you have an area that is a little under or overactive, that TMS could be useful. For example, it's used in fascinating ways in research where there's the right inferior prefrontal is essential for stopping, kind of emergency, quickly stopping something. And if you have TMS to weaken this area, you're much worse at stopping. So you can see it really does have an effect, but it's a very global effect. And so I can imagine there'd be many syndromes where that might not be useful, where you need something more targeted.
Great question.
Thank you. You mentioned that guanfacine can reverse the decline in the dendrite nodes in a prodromal stage. Has there been any research after full onset?
Nobody is doing that yet, so that's why I'm here. I'm hoping these guys in Australia start doing that, but I don't know if guanfacine's available there is one of the problems.
It's not available, really?
I was very curious, again, about the dendrite nodes and the pathology picture. Do you have data with patients that have schizophrenia that are naive to psychotropic drugs and patients that have had exposure to psychotropic drugs? And specifically, is there differences in those drugs, more specifically with patients that have been on clozapine, for instance?
So I am not a physician. I work with monkeys, and so I'm not able to answer that question. I'm sorry.
That's great. Well, thank you. Excellent.